Good morning, everyone, and welcome to the MOXXI Webinar Series, our first installment for the summer edition. I'm Kim, and on behalf of the MOXXI Communications Group, welcome to the MOXXI Webinar Series. For those who are not familiar with MOXXI, MOXXI is the working group under IHS that is tasked to promote the advancement of novel observations, techniques that leads to new sources of information to help better understand the hydrological cycle. And through this objective, we present this year the MOXXI Webinar Series. For the first installment, we have Giulio Dolcetti as our first speaker. And Giulio holds a BSc degree in aerospace engineering from the University of Padua in Italy, a master's degree in mechanical engineering from the University of Ferrara, also in Italy, and a PhD from the University of Sheffield in the UK. Since 2021, he has been a postdoctoral researcher at the University of Trento, also in Italy. Giulio's research focuses on understanding the physical behavior of the air-water interface in rivers, often the most visible yet most elusive part of the water flow. Interpreting water surface dynamics offers a window into key hydraulic and turbulence parameters, as well as interface processes such as the exchange of gas and heat with the atmosphere, and can help overcome some key issues of traditional hydrometry approaches. Notable outcome of Giulio's research include the development of a technique to remotely reconstruct water surface shape via sound scattering, the derivation of advanced Doppler-based surface velocimetry methods using acoustics, and the demonstration of a fully non-contact video-based approach for simultaneously measuring surface velocity and water depth. He is one of the developers of K-Omega, which we also shared in our LinkedIn post, and iWave, two open-source software libraries for physics-based river surface velocimetry. And today, with the topic against the current physics-based non-contact discharge measurements in rivers, without further ado, I welcome Dr. Giulio Dolcetti.
Thank you, Kim. Thanks for the very nice presentation. Thanks to everybody for organizing this, for having me. It's really a privilege to be the one who starts this very nice set of seminars. So thanks to Kim, Tai, Sadashiv, Jorge, Sterja, and to Salvatore, my friend, as well, who had the initiative. Let's see if I can share my screen. Hopefully you would see it now.
Yes, we can see your screen now.
Okay. So what I would like to talk about today is some of the results of my work in the last 5 years, I would say, between the University of Sheffield and the University of Trento. And those were mainly about the physics-based non-contact discharge measurements in rivers. And soon it will become apparent what I mean with that. Let me see if it works. Okay. But briefly, I wanted to give some motivation behind this. So we've seen, and we keep on seeing, following the news, especially in the last few weeks, it's clearly visible to everybody that climate crisis, which is of course due to the human impacts on the environment, is putting our existing river monitoring infrastructure under unprecedented pressure. So we see a higher frequency, higher intensity of extreme events. There is also an increased risks for population assets because population is increasing. We have more urbanization. So the risk, not just the event, are increasing. And in general, the existing infrastructure is often failing at the time where we need it the most, especially the approaches which are based on historical data sets, on fixed gauge station. Those very often are not able to provide measurements of river flow during floods or at the time when we would need it the most. So some a solution perhaps is coming from modeling, and we've seen numerical modeling, but more generally data-based modeling, machine learning methods increasing their capabilities greatly in the last few years, and they're going to expand more and more and become predominant. These methods, they have huge potential, so now we're close to having real-time 2D hydraulic modeling and machine learning. I mean, it's surely going to play a major role in the future. But that doesn't not mean that we don't need data anymore. It's rather the opposite. And I think especially at this stage, when we are transitioning towards machine learning based approach also for monitoring, we need lots of data to train these models, to validate and to calibrate them. And sometimes the kind of data that we need for this purpose is not the same data that we used to need for monitoring data. So we need to also shift somehow the way we approach data collection. In the last couple of decades, we've seen non-contact flow measurement techniques emerging, becoming very well established, and now they are widespread. They are flexible, they're rapidly deployable, they're low cost and safe. Basically, these are methods that allow to quantify the river flow without having to insert a sensor inside the water, but just do it remotely. And this has clearly many advantages. We've seen there are some methods which are based on Doppler. Basically, what they do is they shine some signal against the water surface, then this is scattered, it is reflected back by the moving surface, which means that it will have a shift in frequency. And from this Doppler shift, we can estimate the velocity of the surface. There are different methods, mostly using radar, both handheld and fixed installations. There are also some sensors based on laser, and we've done, basically my PhD was working on ultrasound-based Doppler sensors. These kind of approaches, they're not always cheap. Sometimes their cost can be relatively high, but their main limitation really is the fact that they typically only provide a single point or a single area measurement. So they don't provide a spatially distributed measurement. Instead, non-contact, image-based approaches, and this includes a lot of different methods with different acronyms, LSPIV, SDIV, PTV, or optical flow. Basically, all these methods, they track something on the water surface based on videos. So they detect some features and then compare different frames, and by tracking the movement of these features across the frames, they estimate the surface velocity. These methods have the advantage of providing spatially resolved data. They are low cost, and they are becoming more and more affordable and accessible, also thanks to the advancements with the drone technology and with camera technology. And they are very flexible, so they do have a strong potential to help us address these limitations in terms of measurements and data needs and requirements. However, even these methods, they do have some limitations, or I should say they have some requirements. So first of all, they rely on observing something that moves on the water surface. They require on the presence of tracers and on the fact that these tracers would move approximately at the same speed of the flow, and this is not always the case. And then, as typically what we want to know is the flow rate, is the discharge, then we need to know the bathymetry, and we need to know the water depth. And sometimes measuring this requires direct access to the river with sensors, with operators, which at least partially defeats the whole purpose of non-contact flow measurements. So what I would like to show you in the next 20 minutes or so is how physics-based approaches can provide, can address some of these challenges and can provide an improved approach, especially regarding some of the limitation of existing image-based approaches. The idea of physics-based methods is that we start from an equation that describes a physical process. And specifically in this case, it will be the dynamics of the water surface. And then by comparing with the measurements, we estimate the parameters that define that equation, and from that estimate the flow condition. But it will become, I will show some examples and I will try to explain this, but maybe it's clearer if we show some images. So these were two images of the River Sheaf in Sheffield, taken at different times, about 1 month apart from each other, with different flow conditions. You can see the difference in water depth, discharge, and fluid number. And clearly there is a very strong difference, very clear difference in terms of the water surface appearance. So the water surface responds to changes in the flow condition. This is something that is not currently being taken into account with image-based measurement approaches. But if we are able to understand this response, then hopefully we can, from the video, estimate the parameters of the flow that describe and that cause that response. Before we do that, however, we need to be able to understand the water surface behavior and what drives it. And this is a very strongly understudied topic. So we know very little actually about the behavior of the water surface, how it interacts with turbulence, how it interacts with the current, with the flow in general. But that's because it's a very complicated behavior actually. And if we look at this picture, this was taken from the MOXXI River near Trento, you can see how different the water surface can look like, even with a very small, even at a very small distance between points. So clearly we see very different patterns here. So we still don't know, we're not 100% able to model to understand these patterns, but we know at least how to classify. This is a good starting point. So we know, for instance, that we have some structures called boils, which you can see are these patterns with a sort of a flat region surrounded by small ripples. And we have scarce vortices, these lines or dots or circles, vortex dimples. And all these structures are part of turbulence generated patterns. So they reflect directly the interaction of turbulence beneath the surface with the surface itself. So it's a direct deformation of the water surface induced by the presence of the vortices of the turbulent structures. But also we have waves, and we can see them on the right-hand side of this river, of this canal here. They are similar to the waves we see in the ocean, even if they may look very different. So we see in this case that they are clearly not as two-dimensional, but they have a more of a three-dimensional shape. Sometimes they're not easy at all to recognize, but basically they're always present, always there. And these waves, they behave similarly to the ocean waves, luckily, so we can describe them based on a theory which is a bit more established, and we will see how that can be useful. In terms of monitoring the river velocity, the river discharge, we can expect that the turbulence generated patterns, the boils, the scars, the vortices, that would follow the speed of the flow. That would follow the disturbance, the turbulence which generate them, and just move along the flow with them at the speed of the flow. Waves instead, and we know that from the ocean, they propagate with their own speed. So in the ocean, even if there is no mean flow, waves still propagate with a speed which can also be quite large. And you can see in this case where we don't have a clear direction of these waves that can propagate in all directions. And this can make measurements with the non-contact methods not easy, quite difficult sometimes. So we know, for instance, that waves can strongly bias the measurements of the velocities. They're unreliable LSPIV tracers. And we see in this example by Benetazzo et al., which shows a strong underestimation of the presence of the waves. And we've also done some work trying to quantify the effect of water waves, and we found an uncertainty of up to 100% due to the presence of water waves. So basically from this, we could try to filter out the effect of the waves. This is actually something that has been proposed, has been done. It is a possible, it's a viable approach. But instead, what we try to do is to use the waves in order, and the dynamics and the theory that describes the behavior of the waves in order to understand and gain some information about the water flow. We have to go through just a little bit of theory to describe this behavior of the waves. So you know that waves, they are periodic in time, so they have a period and the frequency, which is the inverse of the period, but they're also periodic in space, so they have a wavelength, lambda, and the wave number, k, which is basically the inverse of the wavelength. So it's like a spatial frequency, let's say. And frequency and wave number, they are related. So the ratio between radiant frequency and wave number is the celerity, it is the speed of the wave. So here, for instance, we have two waves, one with twice the wave number. And if we move, we see that the first one has twice the frequency as well. And the ratio, the celerity is the same. So they have the same speed eventually. What is peculiar of water waves is that their speed, their celerity, is a function of the wavelength. So, or of the wave number. So I'm plotting it here. We can see that in the central region, let's say, the speed of the waves is higher at lower wave numbers. So longer waves travel faster. Then short waves below 2 centimeters of wavelength, they become dominated by surface tension effects. So there is a increase and the minimum of this speed, this celerity of the waves. But in the range that we are more interested about, typically long waves are faster, except when they become comparable in wavelength with the depth. And then there is sort of a capping, there is a limit, a maximum velocity, which becomes equal to the square root of g times the water depth. So in general, their speed depends on both the wave number or the wavelength and the water depth. So if we plot the frequency against the wave number, this is called the dispersion relation, we find we have something like this in still water. It means that if we take any point, we take the ratio between the frequency and the wave number, the slope will be equal to the celerity. Here I called it CS because it's the celerity in still water. And if it's still water, it doesn't matter the direction of propagation. So the speed downstream is the same as the speed upstream. If, however, the wave is propagating above the flow, and the flow has a certain velocity, which is indicated by this straight line here, then the speed of the waves propagating downstream will be faster. So it will be the sum of the velocity of the flow plus the celerity in still water. Whereas if the waves are propagating upstream, their speed will be celerity in still water minus the speed of the flow. And you see that this corresponds to an increase in frequency downstream and a decrease in frequency upstream. So it is like a Doppler effect for the speed of the water waves. So in general, the speed is, the celerity is both a function of the water depth and of the velocity, which means this is a Fourier spectrum of the water surface. So basically, like we do a Fourier spectrum of a signal in time, we see how the energy is distributed between the different frequencies. We do it both in space and in time, then we find the distribution in frequency and wave number. And we can use this to identify the different types of waves interpreting based on what we just saw. So as you can see, there are some structures here that move at a constant velocity, which is not dependent on the wave number. The ratio is a constant here. And these are the turbulent bores, the turbulent generated patterns that move at a constant speed equal to the speed of the flow. But then we also have patterns at a higher frequency, and these are waves which are propagating downstream, so eventually they are faster than the flow. But also we have some patterns here which are more propagating towards the negative wave number, so they're going upstream. And these are basically the Doppler shifted waves with a negative wave number. So from these patterns, we can easily recognize all the different types of waves. What we can also try to do is to, since we can measure these patterns, we can measure these spectra, is to use them in order to estimate these parameters which we assume are unknown at the beginning. So from these measurements, from these spectra, we can estimate the velocity and the water depth. I'll just very briefly show how we can do it. So we start with a collection of images. So it's a set of images of the water surface. So it's a 3D matrix. We have the 2 dimensions in space and time as well. We do a Fourier transform in time and in space in the 2 dimensions. So again, we have a spectrum which is also 3-dimensional. Here I'm showing some cross sections. These are not so straightforward to interpret, but we can focus on this one, which is the cross section along the direction of the flow. So we have our measured spectrum, and we can create a theoretical spectrum as a function of the velocity and water depth, which we can guess at the beginning. And we can basically change these parameters and every time compute the cross correlation between the measured and theoretical spectrum and try to maximize this correlation. Once we maximize it, then we know the water depth, and also we know the velocity and also potentially the water depth. So this is how the whole system works. It's actually quite simple. It has been applied previously, so we didn't reinvent the wheel. There was a first applications. There have been applications in oceanography since 80 years or so. So they've been used, these methods, to reconstruct the shoreline, to plan the disembarkment of troops during the Second World War. But also it's been used to measure and to reconstruct the velocity in the ocean. In rivers, there has been, as far as we know, only one previous pioneering work by Strasser, Carrasco, and Horstmann. This was based on the river Elbe, where there were some wind waves, and they used, as you can see, the same approach of analyzing the spectrum, the frequency wave number spectrum of the waves to estimate the velocity, and they found a very good match between the ADCP measurements and the video-based estimations of the velocity. So Strasser et al., they also released open source code for MATLAB to run this analysis, which I encourage you to check out. Incidentally, there are not one, but 2 more codes, which we've been developing, one for MATLAB and one for Python. The first one is called K Omega in MATLAB and was done by me with Simon Tate at the University of Sheffield and Matthew Perks and Barbara Watubagi from Newcastle University. And then iWave, it's a bit more recent effort, again by me with Hassan Bin Simis from Rainbow Sensing and Salvador Peñajaro from Fortrack. So I will show these QR codes later on as well, but you're very welcome to check them out and test them with your applications. So what I will do now is to basically show some examples of applications of this approach based on these 2 codes, based on these 2 libraries. And the first one is somehow the most obvious one. It's the effect of wind-induced waves. So this is a fragment of a video recorded in the Netherlands in a canal where you can see there is a main flow going from the right towards the left, as you can see from the traces from the foam here on the bottom part of the river of the video. But also you can see wind waves propagating upstream in the topmost part of the video. So if we just apply a standard LSPIV approach in this case, the LSPIV will believe that these waves are good tracers to represent the direction of the flow. And so it would estimate the flow to be going upstream in the on the right-hand side, on the right bank side of the river, which of course was not what was happening then. Instead, if we apply our physics-based approach, in this case it was I wave, you can see how we correctly capture the direction of the velocity throughout the whole cross-section of the river. And whilst with LSPIV, we had a negative velocity in half of the river, basically, so not a good comparison with the DCP. Instead, with I-wave, we get a more decent match across the whole width of the channel. This is another application. This was recorded on River Sarca in Italy. The reason why we took these videos was to do some habitat reconstruction. So basically what we want to do is to fly a drone, and with structure from motion, we want to reconstruct the bathymetry, the detailed bathymetry of the river. And then we use some to the numerical model to estimate how the flow distributes and what that means in terms of habitat suitability for different species. So typically, when we do these recordings, we do them when the water is very shallow and it is very clear, because we need to be able to see the bed in order to reconstruct the bathymetry. However, that is a limitation for image-based velocimetry, because in this case, and you can see it here, you can see that basically there are no traces. All we can see is a slight modulation of the bathymetry induced by the presence of the waves. So it's just the refraction of the water surface that creates this kind of patterns. So if we apply LSPIV to this case, we have these regions where the velocity doesn't look quite right, and basically no velocity estimation at all in the more transparent and shallow and slow areas. If we do the same with K omega in this case, then you can see how we get much more sensible distribution of the velocity, also in the regions where the water was basically all transparent and clear. So again, if we compare with the direct measurements, you can see how LSPIV was overestimating the velocity in most cases, whereas with K omega we got a much better fit with the direct measurements. So far we've seen how these methods can reconstruct the velocity in conditions where standard LSPIV approaches wouldn't work. But as we mentioned, we could in principle also reconstruct the depth. So we tested it, and this was actually the first work we've done with these approaches on two rivers, the River Sheaf in Sheffield and River Calder in Northern in the UK. And in both rivers, we had a fixed camera, which was recording at different times of the day, allowing us to measure many different flow conditions. And here you can see the comparison between the measured water depth and the estimated water depth for both rivers, which was pretty good. And combining the estimated depth with the velocity, we could also directly estimate the flow rate fully remotely, just from the videos. And we compared it with the rating curve, the official rating curves for both rivers based on a DCP. And we had a decent match again in both occasions. Now, you may notice here that the uncertainty of the measurements are larger at the higher water depths. The reason is that the main limitation of the depth reconstruction is that the sensitivity, the effect of depth variations on the frequency of the waves is very subtle. It is very, very small. We can see it here. So by changing the depth by 1 order of magnitude, the correspective change in frequency is quite small, and only long waves with a small wave number actually feel the effect of this change. So in order to successfully reconstruct the water depth, we basically need a very large window. We need to have, which means we have a very low resolution in our measurements. So basically, this is what we did for those measurements beforehand on the river sheaf. We had a window that has a size of 6 meters, which is 1 order of magnitude larger than the water depth. And that's why when the water depth was larger, we began to have higher uncertainties and the method to fail. So this is, at the moment, the depth reconstruction is basically limited to relatively shallow depths. We've done some other tests. This was on River Fessina, which you can see here. It has, again, a combination of different patterns on the water surface. And here we want to do the full velocity and depth reconstruction fully remotely. And here you can see in terms of the depth, how it was reconstructed. So the yellow symbols are the measured water depth. The black circles, the black dots are the reconstruction with our method. As you can see, because of that limitation with resolution, the results are not very robust, especially here in the middle. It was strongly underestimated the water depth, and there is some scattering the data. So what we've been trying to do is to combine this with entropy theory. So the entropy theory basically constrains the distribution of the water depth and also of the velocity in a physical way. And that means that instead of reconstructing the depth at each single point individually and independently, using the entropy theory, we can connect all the dots, basically connect all the points on the cross-section and do a single global optimization and quantify the whole depth distribution based on a single parameter, which is an entropy parameter. And the result is this blue line that you can see here, which is a lot more robust and a lot more stable and compares better with the direct measurements. But the true advantage of the entropy theory is that we can also reconstruct the full velocity profile beneath the water surface, again, in a way which is physically acceptable. So here you can see the comparison between the reconstruction in black and the direct measurements in red. We had some higher uncertainties near the banks because of how the images were recorded, but in general, a decent match. And this means that potentially combining entropy theory, which is also physics-based, with our approach for the image-based, wave-based velocimetry, we can obtain a fully non-contact flow reconstruction in 2 dimensions, which means we can reconstruct the bathymetry, but also the distribution of velocity in the Y and Z directions, all completely remotely without immersing any instrument in water, just from the videos. There are some other applications, not just in rivers. So we were involved in a project in Lake Garda as part of the SAR Lakes project, which aims to quantify currents and waves in lakes. And as part of that project, we had access to a drone, and we flew the drone above the lake surface, and you can see what it recorded. So we see here the waves induced by the wind moving from right to the left. And if you're familiar with LSPIV approaches or similar, you will notice that in this video, there is no reference. There is nothing that we can use to scale from pixel to meters. And this usually means that we cannot reconstruct a direct velocity. We only would know a velocity in terms of pixels per second, not meters per second. This is also something that with physics-based approaches we can overcome. That's because the speed of the waves is a function of the wave number. So it's also a function of the wavelength. So if we compare the speed of two waves with different wavelengths, and we can measure this speed, then we can also estimate their wavelength, and we can use that wavelength to convert from pixels to meters. So if we do this, this is what we obtained. These were 5 different videos recorded from the drone without any reference visible. And we're now trying basically to compare with this with the models and with the direct measurements. However, we have limitations in the fact that the model does not seem to have enough resolution to actually be able to describe these processes. So it's something we are trying to investigate and look at the moment. Finally, all these methods and all image-based methods, they still have one requirement, which we cannot get rid of, and it's the fact that we need light. We need to be able to see the water surface in the visible spectrum. So we try to address this as well. So we use the sound camera, which is basically, it's not really a camera, it's an array of 90 microphones, and each of these microphones is recording the reflection of sound created by a speaker from the water surface. And because each reflection is coming from a slightly different position on the surface, we have spatial and temporal information, which means that basically we can, instead of having the typical Doppler spectra, we can reconstruct the full frequency wave number spectra of the water surface just from the sound without any images and without light. And then if we apply the same approaches, k omega in this case, we can estimate the velocity. And here we found a match between below 15% error in the field as well. So in conclusion, we've seen that physics-based approaches can complement existing non-contact measurements. They can address some of their challenges, some of their limitations. The reason why I gave the title Against the Current of this presentation is because it may seem odd to be going back to the physics, to be going back to the fundamentals at a time when machine learning has become so popular and so widespread. But what I believe is that these methods, so knowing the physics, knowing what is causing the formation of the water surface, can also help us understand what information we could potentially extract from the data. And we've seen an example such as the water depth, but also the scaling of the images. This could also open up new pathways for river observation. And to demonstrate it, I just wanted to leave you with this video. It's also recorded on Salka River. And you can see clearly this boil, which is originating 2-3 meters behind a boulder, which is fully submerged. And basically it's the wave behind the boulder, which is creating turbulent structures. And then these structures have a direct effect on the water surface. So the water surface can really be a window into processes which normally we wouldn't be able to see or to measure or to quantify. And understanding these patterns and gaining more understanding of the physics behind them, I believe that could open new pathways also for estimating the turbulent characteristics and also what happens in terms of the bed roughness and other processes which typically we cannot directly quantify remotely. I conclude with this. Again, if you want to check out the libraries for MATLAB and Python, please feel free. Also, please give us feedback about them. And also should acknowledge the help of lots of colleagues who have been collaborating with in the last few years. And thank you very much. Thanks for listening, and hopefully you'll have questions.
All right. Thank you, Giulio. It's very refreshing to hear about how physics is very interesting in the age of AI, machine learning, and big data, right? Because right now the machine learning community or AI community it's like you see them everywhere. But then at some point, the problem of well, the gaps that we are seeing is that because of all these big data, the quality of the data collected is becoming at some point a problem, more or less, because we're forgetting the fundamentals, which at least
No, please. Sorry.
at least here, yeah, no. At least here we're seeing that with your presentation, it's very important to think about or consider the fundamental, which is in this context, the physics. So, what a great way to start our webinar series. And now I think we move to the Q&A. Well, for everyone, can please direct your questions to the Q&A section, and then I will read them one by one, and then let Giulio answer them. So again, thanks, Giulio, for a wonderful presentation. All right, so for the first question, anonymously, you conducted side-by-side comparisons between non-contact methods such as tracers and traditional ADCP current meter techniques under varying flow conditions. The discrepancies that you observed, how did you address them? I mean, can you, yeah, maybe. The discrepancy between the in situ, I guess, because the traditional ADCPs being mentioned here.
It depends which results we are referring to.
I think they're referring to, well, I don't know who asked this, but correct me if I'm wrong. Maybe they're mentioning between using the tracers for LSPAV and the traditional ADCP. Yeah, it's like between the non-contact and the contact techniques.
I mean, it really depends on the application. So we've seen a few different occasions where traditional image-based approaches, LSPIV, wouldn't work, and we've seen that it is typically because the tracers do not actually follow the speed of the flow, because there are waves or because there is something else. ADCP, I mean, it's very established. It has some limitations which are more due again to where we want to apply them. So in conditions like this shallow river, or also when we did the measurements here on the river Sarka, this is extremely shallow. So if we have a depth of, let's say, 20 centimeters or so, then ADCP, especially if it's a highly three-dimensional flow, it doesn't become viable as an approach. I see all these methods as potentially complementary to each other. I wouldn't say we should get rid of ADCP or we should get rid of LSPIV or anything else. So I think we should improve our understanding of where they're going to work, and we should have more data to compare directly and then understand what data they're given. The main issue with image-based methods is always that we don't know what happens below the surface. We're measuring the surface velocity, and we need ADCP, or we need something to relate that to a depth average velocity, and that we will always need.
All right. Next question. Well, think from Alper LLC. I hope I read that right. How do you compare your approach with satellite remote sensing methods? These have a much higher temporal resolution. For example, the SWAT mission provides frequent surface water level measurements. All right.
I would love these methods to one day become applicable to satellite images as well. I've had some talks with Nick Everard, who is going to present next, I think, at the seminars next month. And I encourage you to take part, because I'm sure you will have a lot of very fresh and good insight on what's the kind of status of satellite-based river monitoring. There is an issue with resolution in space, which depends on the scale of the river which we are looking at. There is an issue with the length of the duration of the measurements, because satellites are passing by so quickly. It's not really the frequency, the rate of the images, but it is rather how long the measurements can be. And because these methods are all in spectral approaches, so what matters is not really the actual resolution or the frequency of acquisition, but it's the spectral resolution. And to have a high spectral resolution, we need long measurements. So ideally, we work with 30 seconds long videos to get a good reconstruction. We can lower it to maybe 10 seconds, but sometimes in 10 seconds, a satellite moves so fast that it becomes difficult to also rectify and keep the images stable and so on, as far as I know. So, but I think there is a potential, and hopefully one day there will be possible to combine them.
Yes. Well, yeah, for satellites, this is still like the gap currently. Okay, next question. Can you please elaborate on the sound camera? It is very interesting, and why this name for the instrument?
And why, sorry?
Why this name? Why they name it like a sound camera? Maybe that's
Okay.
that's the question.
It is called sound camera because it actually has a camera inside there, which we were not using for the measurements. This was a collaboration with Siemens, and they use this kind of device to identify the source of noise, especially in automotive. So they have the camera, and then because of the array of microphones, they can pinpoint the origin of the noise with a very high spatial resolution. And then they overlap it onto the image so that they create these very nice visual maps, which already
It's like
tell
a
you.
map.
Yes, exactly.
Ah.
We did not use that image capability because we worked with very high frequencies where basically we cannot do that beamforming to identify the source of the sound so easily. But we just use the array of the microphones. The main principle is that you know, the Doppler spectrum, even with radar or with any other instrument, changes depending on the angle. So the shift in frequency changes depending on the angle. And it also focuses on specific waves which depend on the position. So basically each microphone at each location is seeing a different mode of the water surface. And then if we combine all of them together, we can reconstruct the full spectrum.
Interesting. Well, this is first time I heard about sound camera, but I heard that there are also some work on trying to reconstruct the bathymetry with this technique. Next question. We have a lot of questions today. I reckon that you would need a stable picture, or at least acquisition position, using a drone, like a fixed elevation and position. What are the minimum technical specifications for the drone for your approach? So maybe he's asking for is there like a height requirement, or maybe a specific drone? I'm not sure. Something like this.
Okay, so the stabilization and the auto rectification is done like with standard LSPIV approaches. So usually I used, for some videos, I used full dial LSPIV for both. For others, lately I've been working more with Pi Open River Cam, which is the software, the library developed by Hasselblad Seniors. It doesn't really matter. I mean, this is not part of the library, so that's something that has to be done externally, but it's sort of standard. compared to standard LSPIV, in the video for these approaches, as I mentioned, maybe we need a longer duration of the videos. And also the size of the windows typically would be a bit larger. So we have a slightly lower resolution also in space. But other than that, the actual resolution of the images can also be low. So usually I work with 8-7 centimeters per pixel, which for some LSPIV wouldn't be very high. It can work both with images taken at an angle or from nadir. Working at an angle, the waves become more visible usually. So it can be more accurate in terms of capability to see the waves. But also, as I showed, it also works from nadir. And with this approach, and this is already implemented in K omega, not in I-wave, so the ability to estimate the scaling, you can just take a video from nadir without any reference, without any ground control points. You can estimate the scaling and directly get the velocity. So maybe you would need ground control points if you want to georeference the images, but you can just analyze any video recording from nadir without that information if you wanted.
I have a follow-up question on this. So if you take it at an angle, then do you need to, when you make the spatial estimate of the velocity, do you need to make a nadir version? It's like, do you need to?
You need to auto-rectify, yes.
Auto-rectify it.
For that, you need to have at least 4 points, which you know the exact coordinates of. But like I mentioned, this is not in our libraries. This is something that has to be done externally, and there are many other softwares nowadays that can do this quite simply.
Yes, but while I'm familiar with a software that we use for auto rectification, but still for this you need the ground control points. So
yes, if it's at an angle, you will need them. Yes, if it's from nadir, you can do without. You can just estimate the scaling. But if it's an oblique point of view, then you need ground control points. Yes, right.
Right, and seems okay. With the emergence of the floods, it feels like it's a hot topic for floods. So the question is, can this technique support early warning system for floods? Or what's your view on that?
I'm not an expert, to be honest, so I focus more on the measurement than on actually what happens during a flood and what could be done. I think it could, like any other measurement approach, like having more data would definitely help us know what is happening. The advantage of this method perhaps is, but that's common of every image-based approach, is that we're not constrained to measuring where we have a gauging station. If there is an actual flood and water is where it's not supposed to be, if it's in the floodplain, we can still go there with a drone and take the measurements and have estimate the velocity. So they have that added flexibility, which I think could be very important. So I believe so, but I'm not the right person to explain how exactly.
I'm not sure in the webinar series if we'll have someone that will cover floods, but maybe we should check. Last question of the day. Are there ideal sites for this approach?
Say it again, sorry?
Is there like an ideal site and is there an ideal site conditions that so you can apply this approach? Are there like minimum site requirements to apply this approach? Like you said, you don't If you do the nadir, you don't need the ground control points. So are there other specific requirements so we can apply your method?
So in terms of the velocity reconstruction, as far as we've seen so far, it works all the time when there is something, there are some wave formations, there are something visible on the surface in terms of that the water is not completely flat, which is almost never the case. Very often there is something and there is some deformation of the water surface. But sometimes, especially looking from nadir, it could be that it's not so easily visible. But as long as those can be seen, the velocity usually can be reconstructed accurately in all conditions. I've seen it struggling maybe with very fast flows, but that's something that can be addressed by changing the resolution of the videos in a way. And also waves, they are always there. It's not just the wind, but in river of all sorts, actually are always found waves. So they are a lot more reliable than artificial tracers. The depth reconstruction, that's a different story. So that it only works in relatively shallow flows, and it only works if the flow is fast enough to generate relatively long waves. So typically, I managed to get decent results in a range of fruit numbers between 0.5, 0.8. For lower fruit numbers, so deeper flows or slower flows, or for supercritical flows, then it doesn't work in my experience. At least now. So we're trying to make it work also in those conditions, but not yet.
All right, we're looking forward to making for you to making it work in the future. So again, thank you very much for the very wonderful discussion and presentation today. Thank you, everyone, for coming.
Thank you. Thanks
Ciao,
for
ciao.
organizing this. Thank you.